In the last class I have discussed that how we can determine the deformation of lateral loaded pile by for single pile, as well as I have given the concept that how you can determine it for the group by using elastic analysis. And for the bearing capacity or the load carrying capacity of the pile I have already discussed for single, as well as the group is the same as we did it for the single. So, now this class I will discuss how we can I will give a solution for the general solution for P y curve. Now, for P is basically stress, Y is the deformation. So, it is stress versus deformation curves for the lateral loaded pile. So, now in this case we are assuming that pile is modeled as beam and which is resting or attached with the spring. Okay. Okay, which is attached with the spring, and we are applying say horizontal load moment at the head of the pile or top of the pile. Suppose this is your y axis and this is the z axis, and this is the value of K h. Okay. Now, if under this condition, that this is subjected to only horizontal load and the moment, and then under this condition the general solution of the beam equation will be. So, that means we are applying this solution will be E p I p d to the power 4 to the y for y z to the power 4 plus k h d y, that is equal to 0. Okay. So, this is your generalized solution for the beam subjected to H and the moment, but here why it is 0? Because there is no UDL is acting. Okay. So, it is only horizontal load and the moment is acting. So, that will be taken care during the application of the boundary condition. Okay. So, this is the common beam equation that I have already discussed, or I have derived even. So, how this equation is coming during my shallow foundation class on beams on elastic foundation. So, you can see those lectures, and then you will find that how these equations is coming. And this equation only difference is that in that case it was only E I, and here it is E p I p, that means elastic modulus of the pile and moment of inertia of the pile. In that shallow foundation case we used K h into B. K into B. B is the width of the foundation and K is the subgrade modulus width of the beam, but here we are using K h into D. D is the diameter of the pile, or if it is a square pile it will be width of the pile. So, this is the equation if no this is the condition that the beam with the spring. Now, if we can go for this is our case 1, we can go another condition. Suppose this is your beam which is again attached with spring, okay. But here it is subjected to H moment plus a compressive load P z. Why this compressive load? Because when the pile will be subjected to lateral load, definitely at the same time pile will be subjected to compressive load, because of the load which is coming from the superstructure or the so that means pile will not only be subjected to horizontal load. At the same time, pile will be subjected to compressive load also. So, in the first case, we have not considered the effect of that compressive load. In the second case, we have considered the effect of that compressive load. So, the basic equation will slightly change. So, this will be the basic equation plus P z d square y d z square plus k h d y, this is equal to 0. So, this P z is the compressive load, which is acting on the pile along with the lateral load or the horizontal load H. So, this is the second one is more generalized equation, because in that case the effect of compressive load is also included, and if you put minus P z, it will be tension under uplift. Okay, but here it is under compression you are talking about. So, now how we will solve this equation? How I solve this equation? So, for the solution purpose, so we have to again we will solve this equation by finite difference technique. Now, when we are talking about this finite difference technique, so we have to divide this pile into number of node points. So, suppose this is the pile and we have to apply the number of node points. Okay. So, this is the number of node points. So, for this is node number 1, 2, 3. Similarly, this is n minus 1. So, we have divided it number of node points with this distance between the node is del z. Okay, this we did it for the beams on elastic foundation concept case also. But here how many boundary conditions are required? So, we need 4 boundary conditions. Okay, so, and there if I express this equation in finite difference form, so these equations will be I can express this equation 2. So, equation 2 in FDM in finite difference method, if I want to express, that will be EP IP divided by del z to the power 4, then y I plus 2 minus 4 y I plus 1 plus 6 y I minus 4 y I minus 1 plus y I plus 2 I minus 2. So, I have already discussed how these equations are coming in finite difference form. Then plus P z divided by del z square, this will be y I plus 1 minus 2 y I plus y I minus 1, then plus k h d y I, that is equal to 0. So, this is the finite difference form of equation number 2, because that is the more generalized equation, because where we have considered the effect of compressive load also. So, now these equation we have to apply on all the nodes. So, that means here you can see there is a term I plus 2, there is a term I minus 2 also. This is I minus 2, there is a term I minus 2 also. Okay, so, there is a time I minus 2. So, that means if it is I minus 2, then if I will apply this equation as node number 1, so then there will be I minus 2. So, that means 2 imaginary nodes will be required if I want to use this equation at node number 1. If I want to use this equation at node number 2, one imaginary node will be required. Similarly, for n if I want to apply this equation at n at node number n, then there will be 2 imaginary nodes will be required. So, n plus 1 and n plus 2, and for n minus 1 node, there will be 1 imaginary node will be required. So, that means 2 plus 2, 4 imaginary nodes will be required, 2 in the in each side. So, that means we have to apply 2 imaginary nodes we have to consider. So, this is 1 and this is 1. So, this is 2 dash and this is 1 dash. So, now for point node number 3 to n minus 2, you can apply these equations, no issue, no imaginary nodes will be required. But so that means here also there will be n plus 1 dash, then another equation n plus 2 dash. So, this 1 dash 2 dash or n plus 1 dash n plus 2 dash, these are the imaginary nodes. Okay. So, and you know that these nodes, because these are not the real nodes, they are the imaginary nodes. The deflection of these nodes, we have to convert it to the deflection of the real nodes, and that you have to do by using the boundary conditions. Now, what is those boundary conditions? So, that means here how many boundary conditions will be required? This is 1, 2, 3, 4, 4 boundary conditions will be required. So, for the boundary conditions, okay, first we will go for the free headed pile, then we will go for the fixed headed pile. So, for the free headed pile, that your at the tip of the pile, that means at the base of the pile, shear force will be equal to 0 and moment will be equal to 0, because the tip is considered as a free end, because it is at the within the soil and it will be considered as a free end. So, we can take this is the slope will be 0, moment will be 0. So, that is the condition for free end. So, that means for free ended pile, both the ends will be treated as a free end, and for the fixed headed pile, the top end will be treated as a fixed and the bottom end will be treated as a free end. So, if it is shear force and bending moment is 0, so I can write that if Q is equal to 0 and M is equal to 0. So, for the moment part or the shear force, I can write that this is E p I p d 3 y d z 3 plus p z d y d z, that will be 0 at z is equal to L. Z equal to L, L is the length of the pile. Okay, Z is the length of the pile. Similarly, for moment is equal to 0, I can write that E p I p d square y d z square will be 0 at z equal to L. Okay. Now, at the free end of the pile, so here the shear force will not be equal to 0, because the shear force, there is a horizontal force is acting, because as I mentioned, we have incorporated the compressive load effect in the equation, but we have not incorporated the H and M effect in the equation anywhere. So, that H and M will be incorporated through the boundary condition. So, for the free end of the pile, your this shear force E p I p d 3 y d z 3 plus p z d y d z, that will be equal to H. that will not be equal to 0, because now a horizontal force is acting. So, that is at z equal to 0. Similarly, for the bending moment, E p I p d square y d z square, that will not be equal to 0, that will be equal to m 0 at z equal to 0. So, this is the free end pile. So, this is the free headed pile. Now, for the fixed headed pile, your the shear force for the fixed headed pile, that shear force equation will be same as this equation, E p I p d 3 y d z 3 plus p z d y d z, that will be equal to h at z equal to 0. Okay? But dy dz will be 0 at z equal to 0, because in fixed headed pile moment will not be 0. Shear force will be that shear force that is developed, but moment will not be 0, because for the free headed pile we put moment is also applied some moment, but here the condition is that for the fixed headed pile, one is the shear force equation that I have written, another is due to the slope at that z equal to 0 will be 0. So, this is from the slope consideration, this is shear force consideration, so this is shear force consideration, this is the bending moment consideration, this is shear force, this is moment. Okay, this is the at z equal to 0, and for at the tip of the pile, the boundary condition will be same as the free headed pile. So, that means at the tip of the pile, this will be E p I p d 3 y d x 3 d z 3 plus p z d y d z, that will be 0 at z equal to L, that is shear force consideration, and E p I p d square y d z square will be 0 at z equal to L, that is bending moments consideration. Okay. So, you can use these 4 boundary conditions for free headed pile and the fixed headed pile, and then you can solve this equation and you will get the deformation, or once you get the deformation, then you will get the bending moment, slope, shear force, whatever you want. But the one thing I want to mention, that what would be the suppose if you want to use the kh variation. Okay. So, the one variation will be that you can simply write that my I can consider that kh variation, so variation of kh. So, kh here we have not talked about the kh variation. So, what will be the kh variation? Now, kh variation will be linear, then in that case that p will be kh into y. Okay, so, that means that at any point that p stress is linearly varying with the deflection. Okay, so, that is the linear variation, or I should write. So, no, this linear variation I will write later on. first I am writing the kh, variation of kh. So, variation of kh can be in different types. So, this is the kh is equal to eta h, then z by d. So, that is one variation we have already used. So, this variation is linear. So, kh is varying linearly with depth. Okay. So, previous solution. So, this is the variation. So, another variation can be that kh is equal to eta h z to the power n by d. So, now if n is equal to 1, then this will be the linear variation, which is same as this one. But if n is greater than 1, then it will be not a linear variation, it will be a non-linear variation. Okay. Or for non-linear variation, you can write kh in different form, that is 1 by d k 0 plus k 1 z plus k 2 z square. Okay. So, these also you can write in different form. So, this is the different variation of the kh. It can be linear, it can be non-linear, depending upon your requirement. You can put them in the equation, because now it is so flexible that you can put the different variation at your in the equation, and you can apply this variation at different nodes, and you will get the your result by using the different variation or the variation you want. Okay. So, then the PY relationship, that is the stress and the deflection relationship, or the PY variation, I should say, and P is the stress, Y is the deflection. So, the linear variation is that P is equal to kh into Y. This is the linear variation. Then the non-linear variation also, that means P is equal to kh y to the power n, or P is equal to k z to the power m y to the power n. Okay. So, these here this k, m, n are the determined coefficient. So, this k, m, n are the coefficient, those can be determined experimentally. So, that means here not only you can give different variation of kh, but you can give the different variation of the py. That means, whether you will put a linear variation, that means in previous expressions that k, that means here the stress strain behavior or the load settlement behavior is linear, but you can put non-linear variation also. Okay. Because this is the first one is the linear variation, second are the non-linear variation. So, that means here that beams are not only resting on the linear spring, that means it can be resting on the non-linear spring also. That means you can incorporate the non-linearity in the load deformation behavior. You can put the non-linearity in the variation of the kh along the depth. So, this variation of the kh is along the depth. So, that we can incorporate in this equation, and then we can solve it. Okay. And another thing is that as yes, so as you know that your this that means kh value is not constant with the depth. It is varying for this granular type of soil. So, you can vary this kh, and if you want to make it uniform, because for the cohesive soil it is uniform, then you can make these things uniform also. Even this stress strain relationship or deformation and the load versus deformation or the stress versus deformation relationship also changes along the depth. Okay. So, deformation versus your load or the load versus deformation behavior, that also changes along the depth. So, that also you can incorporate here, because as I mentioned, for different node you can put different variation, and if you decide to know there will be different variation and different node, that also you can incorporate here. So, that means all this type of flexibility are there in this type of solution, where you can put a different variation of kh along depth, you can different variation of p and y, you can put it linear, non-linear, or you can have a py variation along the depth also. So, those things you can incorporate here. And another thing I want to mention, that if you put pz equal to 0, then everything will be converted to equation number 1. So, if you put pz equal to 0, then everything will be converted to equation number 1 or your case number 1, here it is case number 2. So, that case 2 is the most generalized solution, where we have taken the consideration of the compressive load along with the lateral load. So, this way you can get a solution, and then you will get the deformation in the other quantities. So, this is the end of this lateral loaded pile part. So, now I will start the next topic, that is the uplift pile under uplift load. Okay. So, now as I mentioned, the pile can be under uplift load also, and that uplift load means when suppose pile is a transmission tower, where pile can be uplift load. Suppose if this is a transmission tower and this part of pile and this is the pile, and when there will be wind force is acting in this direction. So, it will try to rotate this structure. So, that means this portion of the pile in such case will be under uplift, and this portion of the pile will be under compressive load. And this can be reverse also. If the direction of the wind will changes, then the direction of this uplift and compressive, that will also change. So, that means when you check a pile under uplift load, at the same time you have to check it for under compressive load also. So, now first I will discuss that how I can develop the equation for the pile under uplift load. So, that means pile under uplift load, that PUG, that means pile under uplift. Okay. So, that is your, or this is called gross uplift load. So, that will be equal to PUN, this is net uplift plus W. This is gross uplift capacity, I should say, gross uplift capacity, net uplift capacity, and this is weight of the pile. Okay. So, this is the equation, that means when pile will be subjected to uplift load. So, in that time this tip resistance will not be active. So, only the skin friction will be active. Okay. So, it is acting this direction. So, skin friction will act in the downward direction, but the tip resistance will not be there. So, this is your PUN. So, that means PUN plus W will be equal to PUG. So, now for the clay, how we can calculate PUN? PUN will be equal to alpha dash Cu into the perimeter into the length. So, that means here P is the perimeter of the pile and Cu is the undrained cohesion L is the length of the pile and alpha dash is the adhesion factor. Now, how alpha dash can be calculated? Alpha dash is equal to 0.9 minus 0.00625 Cu, that is for cast in situ pile and if Cu is less than equal to 80 kilonewton per meter square, and this is equal to 0.4 minus 0.4. This is for cast in situ and Cu greater than 80 kilonewton per meter square. Now, for pipe pile, this alpha dash is equal to 0.715 minus 0.0191 Cu for Cu less than equal to 27 kilonewton per meter square, and this is equal to 0.2 for Cu greater than 27 kilonewton per meter square. So, this way we will get the adhesion factor, and if you know the undrained cohesion, if you know the length and perimeter, we can get the PNU, and at the same time we can calculate the weight of the pile and you will get the gross uplift capacity of the pile. Now, for the this is for the cohesive soil. Now, for the granular soil, how we can calculate this value, and so that means for the granular soil there will be again the critical depth we have to calculate. So, this is the critical depth where this is I critical or L critical, this is L minus L critical. So, this is for the granular soil or sand. The initial was for the clay and this is for the sand. Now, how I will calculate the critical length? So, this chart will help me to determine the critical length. Suppose if I know the relative density of the soil and if I know the and then for this particular chart corresponding to relative density will give me the critical length divided by diameter, L by D critical length. So, that means for it is varies from say this is the critical length axis, this is the delta by phi axis. So, in this axis we will find for say 80% relative density, it is around this is 12, 13, 14. This is 12, 14, 14.4, 14.5. So, that means the maximum value is around 14.5 for the critical length. So, that means L divided by D critical maximum is equal to 14.5 for uplift case, because for compressive case we that means for loose sand we took a critical length by D ratio is 15 and dense sand we took it for 20. But here it is dense sand, it is 14.5 and for the loose sand around this value you can say this is around 10 or something. So, that means for the it varies from 10 to 15. So, slightly less compared to the pile under compressive lead. So, first you will calculate, we have to determine the critical length, and then here we can calculate the delta by phi for different relative density also by using this chart. Suppose if it is 80% relative density, then this chart we use. So, delta by phi is around 1. So, this value is 1 for 80% relative density. Okay. So, that means for 80% relative density it is 1, for 40% relative density it will be around 0.88. So, this will be 0.88 for 40% relative density. So, this chart is for relative delta by phi, this chart is for critical length, and this axis is for the delta by phi axis, this is for critical length axis, and this is the x is the relative density. So, that means finally, for granular soil, that P net ultimate for this type of case we can determine. Suppose this is at the critical length, this is P1, and that will continue here. So, for this particular case it will be, this will be half into P1 into L critical, okay, and then there will be Ku and delta, tan delta, okay, then plus and then there will be perimeter into length. So, that means and then for rest of the portion there will be P1 into L minus L critical, L minus L critical into Ku into tan delta into P into L minus okay. So, this is will not be there. Okay. So, that means finally, I can put here the equation is that half into perimeter into P1 is the stress at this level, okay, into Ku into tan delta into L critical plus perimeter P1 into perimeter into Ku into tan delta into L minus L critical. Okay. So, now if P1 is equal to gamma into L critical. So, finally, if I put this value here, this will be half, or I should write gamma dash, this will be perimeter gamma dash L critical square, then Ku tan delta plus P gamma dash L critical Ku tan delta into L minus L critical. So, this is the equation of the PNU. Okay. So, once you get the PNU or the net ultimate resistance for the granular soil, then you can calculate what will be the gross ultimate load carrying capacity or uplift capacity of the pile. Okay. So, this is yes, this is the equation. Now, let me solve one particular example problem. So, this example problem will help you to determine the or to know the uplift capacity of the pile. So, for the diameter of the pile was given 0.4 meter and the variation is, this is the water table this is the critical and this is the uniform. So, this is the 3 variation. Here the water table is present here, which is at a depth of 2 meter. Diameter is 4 meter. Okay. Then the length of the pile is 20 meter. Then gamma sat is given 19.5 kilonewton per meter cube. Gamma bulk is given 18 kilonewton per meter cube. Gamma concrete is given 24 kilonewton per meter cube. Phi value is given 38 degree. Corresponding relative density RD is given 70%. Okay. So, RD is given 70%. So, RD is given 70%. So, what would be the critical length? So, which is again 14.5. Okay, the same 14.5. So, corresponding L by D critical, that will be 14.5. So, L critical will be 14.5 into 0.4, which will be 5.8 meter. So, critical will be up to this, which is 5.8 meter. So, that means the distribution will be something like that, and then there will be uniform. So, this is how much? So, this will be 3.8 meter. Okay. And then rest will be the uniform. Then delta by phi, will be how much? This is for 70% relative density, delta by phi value is close to 1. So, delta by phi is close to 1. So, that value is close to 1. Okay. So, delta is equal to phi, which is equal to 38 degree for 70% relative density. Now, weight of the pile will be pi d square by 4 into L, L is 20 meter into the density, which is 24. So, this is 60.3 kilonewton. So, P net ultimate, if I calculate from 0 to 2 meter. So, 0 to 2, this is the gamma bulk is 18 and it is into 2. So, that will be 36 kilonewton per meter square. Okay. 36 kilonewton per meter square, and this point, this value will be 36 plus this is SAT is 19.5 minus 10 into 3.8. So, that will be equal to 72.1 kilonewton per meter square. So, we have considered unit weight of water is 10 kilonewton per meter cube. So, for this particular part, this will be half into 36 into Ku into 10 delta into perimeter. Okay. So, half, because we have taken the average, that is into a perimeter, or we can write that is equal to half into 36, and Ku value is how much? Ku value is phi is 38 degree. So, Ku is here, this Ku will be 2.3. So, I will take Ku is equal to 2.3, tan delta is tan 38 degree, then pi is 3 perimeter into length. So, this is perimeter into length, because or you can put length here also, half into that 36 into L, then Ku into tan delta into perimeter, that also you can write. But remember that this equation that I have developed in this slide is applicable if your unit weight is uniform. If the water table is at the ground surface, then you can use this equation directly. But if it is not uniform, then first you draw the pressure distribution, then calculate segment wise, like this what I am doing. If the unit weight is uniform, then you can use those equation directly, otherwise you have to do it segment wise. So, that is 3.14 into 0.4 into 2, that is equal to 81 kilonewton. Then P net ultimate 2 to 5.8 meter. So, that is half. Now, it is half, we are taking the average, the same thing that we did for the pile under compressive load to determine the friction resistance. So, this is half, then 36 plus 72.1 into 2.3 into tan delta is 38 degree into the perimeter. Perimeter is 3.14 into 0.4, then into 3.8. 3.8, this will be 464 kilonewton. Then P N EU for 5.82 rest of the pile 20 meter, that is equal to, again that is uniform. So, this will be 72.1 into 2.3 into tan delta 38 degree into 3.14 into 0.4 into the length, which is 20 minus 5.8. So, this value is 2311 kilonewton. Okay. So, total P NU will be 28, that will be 81 plus 464 plus 2311. So, this will be 2856 kilonewton. So, the gross will be 2856 plus 60, this will be 2916 kilonewton. So, this is the uplift capacity of the pile for granular soil. Okay. Similarly, you can calculate it for the cohesive soil also. So, that means remember that the equation that I have given directly you can use for uniform unit weight. If there is water is there or it is not uniform, then you have to do it segment wise, but you have to consider the critical length that I have discussed by using these two charts. So, this is the end of this pile part. So, next class I will start the new topic, which is the well foundation, and then there will be one more topic, that is foundation on difficult soil. Thank you.